Alright, let's zoom in over here on Ohm's law. We're going to deal a little bit with Ohm's law first, and we'll deal with inductive reactance, and we'll deal with impedance. We're looking here at Ohm's law and how Ohm's law works. We talked a little bit ago about voltage, amperage, and ohms. Okay? Volts are the pusher, amps are the electrons, and then resistance is just because it's that material and it has some natural resistance to the movement of those electrons. Okay? So, if we were looking at Ohm's law triangle here, we would say if we want to calculate for volts, we would cover up the E and it would be I times R. Okay? If we were going to calculate for I, it'd be E divided by R. Same way with R, E divided by I. Okay? So, knowing what these stand for, if we were to plug in an equation here, looking at number 1 that you guys got, it is E equals blank, I equals 6, whoops, I can write, R equals 2. Each of these are units, so that's volts, that's amps, and that is ohms. Okay? So if we're looking for a volt, we have 6 amps and 2 ohms. It's going to be 6 times 2. Our voltage is going to be 12 volts. Okay? Very simple. I don't think there's any question about Ohm's law, and it works in any direction. So let's just say for fun here, we were given 12 volts. We were given 12 volts and 3 amps. How many ohms of resistance are we going to have? We're going to have 12 divided by 3. That's going to equal 4. Okay? Very, very simple there. And remember, these are all units again. Volts, amps, ohms. Okay? I don't think you should have any questions there. That one's pretty simple. Some of them you don't even need a calculator for. So let's push over to inductive reactance here. I got to come back around and move the camera so I can actually see something and you can see something. So there's our inductive reactance. Okay, it's a little more involved. Not too much, but just a little bit. That's going to tell us that inductive reactance, which you already know what that term stands for. That's the time delay it takes for a coil to interact against itself and for everything to kind of null out. That's inductive reactance. That's going to equal 2 times pi times the frequency of our test times microhenries. Okay, this microhenries is a given value for a specific material. That's the resistance value that's already there. We're going to multiply all those across to figure out an inductive reactance value and what that inductive reactance value is going to do for us. Okay? So, X sub L, or inductive reactance, equals 2 times pi times the frequency of our setup, which is 100,000 hertz, times 0.123457 Henries. Okay? And then real easily, if I had my calculator, I placed it over here, we could go, if you've got your calculator, 2 times pi times 100,000 times 0.1234575. That's going to tell me 4.712 ohms. Okay, there's a bunch of math that goes in behind it to get all of these numbers. Okay, this is a constant, this is a constant, this is 100,000 hertz, and this is henries. Okay, so all these multiplied together are going to leave us with ohms. We're not necessarily concerned how that comes about. We just need to know that it winds up being ohms, because we're going to take an ohms value from here for resistance, an ohms value here for inductive reactance, and we're going to put those 2 ohms values together for impedance. Okay? So as you can see, that's just a straight multiplication through. Again, this was pi, this is frequency in hertz, and this is henries. Okay, and that's that inductance value for each material. Alright, so let's make our last move over here to impedance. Okay, we're going to take the 2 that we've already used, Ohm's law and inductive reactance, and we're going to put them into an impedance equation. Formula. You say equation, that freaks people out. So, here's my notes, or here's my book of all the problems. So we're going to take these values. We've got impedance, okay, impedance, inductive reactance, resistance. Quite simple. So the first one here is the square root of 489, so that's going to be squared, plus plus 580 squared, and that's going to give us some value. Now, if you looked way back when, I think I've got a little room over here still. So if you looked way back when, we talked about AC current just a little bit. Okay, in your book it showed you a little picture like this. So here's current due to resistance. Okay, there's no movements, no shifts. There's a little bit of inductance. Okay, so current due to inductive reactance. That's here. Okay, so this is regular current. This is current due to inductive reactance. So there's a little bit of a lag here. Okay, the lag in time tells us that something happened to slow that current down and started at a later period. Okay, so inductive reactance did that to us. Now, if we took both of these terms, regular current and current due to inductive reactance, and combined them, we might wind up with something like this. Okay, with a larger value than both that we even started with. Okay, winds up larger. So this is current due to impedance. Alright, so let's take a look at that here. If we've got 489 squared plus 580 squared, that's going to equal 575,521. We're going to square root that. That brings me down to 758. So I'm going to say these two right here, 575, 521. Then I square root that. That brings it all the way down to 758 ohms. Ohms, ohms, ohms. So this would be here. Current with resistance, that's 489. Okay? Current due to inductive reactance, that's 580. I lied, I got those backwards. So 580 to start for a regular old current due to resistance. 489 due to inductive reactance, and then overall we wind up with a total of 758. Now what that actually looks like is this. If we plotted that on a vector diagram, which you saw just a little bit of this, and we had a value, inductive reactance of 489, okay, a value over here, resistance, that's going to be 580. We combine those two together. Okay, if we did Pythagorean's theorem, that would let us, let's get that out here a little farther, that would let us triangulate this, and we would wind up with an overall value up here of 758 ohms. Okay? So, pretty simple. Now what that actually represents to us right now is not a whole lot, except for the next couple videos are going to be about movements, shifts, stuff like that. We're going to look at when you start off, and then you have the impedance of the coil in air. Then you take the coil and put it down on something, the impedance is going to shift. So when you have a shift in the coil, you're going to have a shift, maybe from here on your screen down to over here, or up to here, or down over here somewhere. Okay, it doesn't really matter, but we're going to look at the difference between those shifts. Okay? So soak in that math for just a second, and then we will move on from there looking at a couple of terms about eddy current and how they're affected on the scope.